Hi everyone. Good afternoon. Today I will talk about our work on detecting driver phone use leveraging car speaker, and this is joint work with Simon Hongbo Liu, Professor Yin from Stevens Institute of Technology, and also collaborate with Gary Tan, Nico, Professor Michael Professor Rich Martin from WINLAB Rutgers University. So, distinguish driver and passenger phone use can enable lots of applications, but its greatest promising lies in help reduce driver distractions. And the driver distractions have been involved in many high-profile car accidents associated with a large number of automobile accidents. For example, if you use cell phone texting, handheld cell phone while driving, this will cause manual, visual, and cognitive distractions, which means it makes you hands off the wheel and makes you eyes off the road, and also makes you your man of the driving. And further, if you're talking on the phone, it will cause visual and cognitive distractions. And some people argue that by using the hand-free cell phone, it can mitigate the driver distraction. However, recent research shows that it actually causes cognitive distraction, which means it makes you your man of driving. So this will increase the accident risk. And among all these cell phone distractions, there are 18% of drivers that admit to texting while driving, and whereas there are about 91% of drivers that admit to talking while driving. So as the cell phone distraction, it's actually cited as #1 distraction among all kinds of driver distractions, such as drinking while driving, operating CD, radio while driving, and using cell phone while driving is 4 times as likely to crash compared with normal situations. And during 2009, according to the National Highway Traffic Safety Administration report, there are 995 people who were killed during the because of cell phone distraction, and there are 24,000 people get injured because of cell phone distraction. As a result, cell phone distraction has been increasing public attention. In the United States, there are 7 states ban handheld phones for all drivers, and 21 states ban for novice drivers, and there are 19 states ban texting while driving. On the other side, there are lots of recent works in developing some technical approach to prevent cell phone use when cell phone is used in vehicle. For example, once the cell phone is detected in a moving vehicle, the software will route the incoming call to voicemail or deny the incoming text notification, or actually it can send an automatic message to the caller saying that I'm driving, and call me later. Even some approach using kind of hardware to send jamming radio to jam the cell phone use. However, for this approach, it mainly detects the phone, whether the phone is in a moving vehicle or not, by using some techniques such as by using GPS, embedded in phone, or handover from cellular network, and some other techniques such as use signal strings to deduce whether the phone is in moving or not. However, the drawback of this method is that it cannot distinguish driver phone use and passenger phone use. And according to the report from the Safety Administration, there are about 39% of automobile trips include passenger. So if once you detect the phone is in vehicle, you broke the phone, then it is probably unacceptable for this passenger phone use, and this causes high false positive rate. And there are some existing approaches that can be used to detect the driver phone use. For example, there is work in detecting speaker location inside a car by using a microphone array. For example, you can detect which speaker emits the sound signal by using microphone array inside a car. And even some other method using a specialized antenna attached to driver's seat so as to detect whether the current phone use is by passenger or driver. However, for this method, it needs additional hardware infrastructures and also involve expensive computational costs. In our work, we actually using an acoustic ranging approach. It performs ranging between the cell phone and the touch speaker, so there is no dedicated infrastructure. And the requirement is that the phone should be able to access the car's head unit via Bluetooth connections. And now there are more and more cars equipped with Bluetooth technologies. And in industry report, there will be 90% of cars equipped with Bluetooth radio systems in 2011. And further, based on the ranging between the phone and the speaker, we can classify which car seat of phone is being used, and this can leverage by the symmetric position of speakers. If the phone is close to one speaker, then we can classify which seat the phone is being used. So, before we can classify the phone's location seats, we actually need ranging information, which is distance difference between the phone and the speakers. And next, I will introduce how our system works in high level by using acoustic ranging-based method. For example, this is a car with 4 seats, and I first introduced this with car's 2-channel radio system, since there are a large portion of cars currently only equipped with 2-channel audio system. Suppose our system can be triggered by an incoming call or incoming message, or actually it can be triggered once you detect the phone is in vehicle. Suppose at time point T1, the cell phone sends a beep signal to the speaker via the audio head unit, and this connection between head unit and the cell phone is through Bluetooth radio. And after a time period delta t, at time point T2, the cell phone will send another beep sound to another channel of car's audio system. Suppose it's speaker Y, S1. And after the phone sends out the beep signal, short after this operation, suppose at time point T3, the cell phone can record back the emit beep sound from the first channel. In this case, it's from speaker 2. And after a short time period, delta T1, the cell phone can record back the beep signal emit to the second channel, which is from speaker 1. And we can calculate the delta T1 and the delta T. Delta T is predefined. By comparing these two values, we can say if this value is the difference between delta T1 and delta T is larger than 0, it means that the cell phone is closer to speaker 1. If it's below 0, it's indicated it's close to the speaker 2. And if there is 4-channel audio system available on the car, we can say that we can send another 2 beep signals to the 3rd and 4th channel. And similarly, we can record the signal beep from the 3rd channel and the 4th channel. Similarly, we can get the delta T2, and we compare delta T2 with predefined time interval delta T. We can deduce whether the phone is closer to speaker 3 or close to the speaker 4. By using this acoustic range-based method, we can finally classify whether the phone is located at the driver's seat or at the passenger seat. However, there are several challenges in this acoustic approach. The first one is unobtrusiveness, which means we want the sound emitted by the system not perceptible to the human ear, so that it will not disturb the driver. Second is that in an in-car environment, there are lots of heavy multipaths, and also when car is driving, there will be lots of noise coming from engine, wind, and music playing, conversation. So this acoustic-based approach should be able to robust to noise and multipath. The third is that the approach, the ranging approach that should be feasible of the shelf smartphones. So this means that the signal processing technique and the ranging method should not have a heavy computational cost. And we first talk about how we design this beep sound. Since that the first step is of our system is that the phone needs to emit beep sound to the car's head unit. And we first consider 2 challenges, which are background noise and inaudible beep sound. So to achieve to roast to background noise and make the beep sound inaudible, our approach is that we choose high frequency beeps. So let's first look at the noise source, which are engine noise, tire road noise, wind noise, conversation, and also music. And suppose if the recorder on the cell phone is set as 44 kHz, it can support the sound signal up to 22 kHz frequency. So in this frequency band, first the engine noise is mainly located below 1 kHz, and the conversation is usually located between 300 Hz to 3.4 kHz. And if we look at the music, it has much broader frequency range, usually located from 50 Hz to 15 Hz. So by looking at this frequency band that this noise is located, we can say that at the frequency band from 15 to 22 kHz, there barely have any kind of noise. So this frequency band is a good candidate of our beep frequency range. Next, let's look at the inaudible, how we can get inaudible beep sound. First, the strategy we choose this beep sound is that we want the beep sound is close to the limits of human perceptions, and this limit is at around 80 kHz. And also, we need to make sure that the cell phone's microphone can record such high frequency. So let's first look at the absolute threshold of hearing graph, which shows that that's the minimal sound pressure that's required for human to perceive the sound under different frequency. And this x-axis shows the frequency from 0 to 20 kHz. The y-axis shows the sound pressure, and we can say that human ear is sensitive to the frequency band between like 2 to 10, and this threshold decreasing sharply after like 20 kHz. And we can compare this to the frequency response of cell phone's microphone. And this figure shows the frequency response of iPhone 3G and Android developer phone 2, these two phones. Blue line shows iPhone, and the dotted red line is for ADP2 phone. And we can see that at this high frequency range, say around 80K, the iPhone has relatively good frequency response compared to the absolute threshold of hearing graph, which means we can utilize this frequency sensitivity gap between human hearing and the frequency response of cell phone to both record the beep sound emitted from the speakers, and also make this beep sound inaudible insensitive to humans' hearing. And in this case, for the iPhone, we choose the frequency band between 80K to 20 kHz, and for the ADP2 phone, it has a little bit worse frequency response, and that's we choose the frequency band between 16 to 18 kHz. So after the beep sound emitted from touch speaker, the cell phone will record back the beep sound, and then perform beep signal detection. So we want to detect when the beep signal is arrived, so as to get the range information between cell phone and touch speaker. Commonly used method to detect the beep sound is in time domain, which means this approach want to coordinate the beep sound with the recorded sound. Once the coordination at a certain time point, if the coordination between this beep sound and the recorded sound reach maximum value, it will determine that that time point should be the signal that first arriving signal that in the recorded sound. However, since that in the heavy multipathing time environment, the signal will be significantly distorted by this multipath. And the second is because we use a high frequency beep sound, and this will lead to distortions because of reduced sensitivity of microphone's frequency response. So it makes it hard to detect the beep sound in the time domain. We take a different approach by detecting the beep signal in the frequency domain. What we want to do is that we want to detect the first arriving signal, other than compare the whole beep signal to the recorded sound. Which means in this case, even if there is multipath, as long as there is if we detect the first arriving signal, as long as there is signal reach the cell phone, we can declare the detection of signal. And first, since we choose high frequency band as a beep signal frequency band, so we can apply a short Fourier transform in each moving window to extract the energy at the target frequency band, which is beep's frequency band, so as to filter out this energy located at the noise frequency band. Second, we use a signal detection method to identify the first random signal that deviates from noise. That's the basic idea. And the problem formulation is that suppose we get a sequence of measurement after filtering, say it's X1.
At the conference, you would have 2 more minutes if I'm watching the time correctly. So somebody else.
Yeah, no, it's not right. I have 5 minutes.
Okay. So
probably want to just skip this slide.
Well, why don't we go ahead and give it, and then we'll record the time for the minutes. We're going to figure out what to cut.
okay. So suppose we have a sequence of recorded audio signal, and then what we want to do is that based on the observed sequence up to time point t, x1 to xt, we want to identify whether xt is noise or xt is beep signal. And we adapt the change point detection method to detect this, to perform detection of this first random signal. I will talk about the idea using this illustration. So suppose this is a signal recorded after filtering. X-axis is time, y-axis is amplitude. And first we can use the first part of the signal that we are sure it's noise to estimate the noise mean and standard deviation. And based on this noise mean and standard deviation, we calculate the cumulative sum of difference between the signal and the noise mean. So we get a metric which is SK, which corresponding to the first graph. And then given a threshold and the Ross window, we can detect that once the signal is above the threshold and the later part of signal is still above this threshold, we declare that the beep signal is detected. So here is the walkthrough of the architecture system. First, we insert we choose frequent beep sound at very high frequency. And the frequency is simply frequency for the sound is 44.1 and support up to 22 kHz, and it's 60 to 80 K for 82 ADB2 and 18 to 20 for iPhone 3G. And among this frequency band, the sound energy is uniformly distributed over this entire beat frequency range. And the beat length is set as 400 samples so as to make sure the phone can record it, and also it can robust to multipath. And the time interval between two emitted beep is 1,000 samples, so as that this beep from different channels will not interference with each other. And in order to get a more robust results, we insert 4 beep at each channel, and this can robust to 2 outliers. Okay, that's the first step, emit beep signal. The second step is that the phone will use the sampling frequency 44.1 kHz to record the emitted signal, and this sampling frequency is widely supported by smartphone. And this recorded signal has natural distortion, and also it's the combination with the beep signal and the noise, such as music. And the third step is that we apply short Fourier transform to filter out the noise located at the noise frequency band, and the short Fourier transform window is 32 samples, and we apply a moving window to perform short Fourier transform so as to get a more detailed, more fine-grained granularity. After filtering, we use checkpoint detection to detect the signal. And the criteria for the threshold is that it's the noise mean plus 3 standard deviation of noise. This is equivalent to 99.7 confidence level of noise. And the loss window is set at 40 samples, which means that after this detected signal, you need to make sure that the later 40 samples will also match that threshold. After that, we can give in the predefined delta t, which is 1,000 samples, and also the after we detect the random signal, we can calculate the time difference, which is delta t1. Based on this two, we can calculate relative ranging, which is delta t1 minus delta t. And this delta t is measured by the sample counting technique. And next, based on this relative ranging, we want to classify whether phone is located at driver's seat or not. If with two-channel system, we can only classify whether the cell phone is close to the driver's side or it's close to the passenger side. However, if we have a 4 radio system, we can get the ranging from the third and fourth channel, and further we can classify whether the cell phone is close to the rear, the back right seat or the back left seat, so as to locate the cell phone's seat. Okay, that's the basic flow of our detection system. And we performed the evaluation in using 2 different phones and in 2 different cards with different cards. First one is phone 1, ADB2, which has Bluetooth, like 192 RAM and 528 record processor, and another phone is iPhone 3G. And we have 2 cars, which are Honda Civic, and the other one is Acura Seda, and these 2 all have Bluetooth radio and with 2-channel radio system. And the dimension of these 2 cars are different. The first Honda Civic is smaller than the second Acura. So to simulate the 4-channel system, we're using head unit fader system. So we first emit 2-channel. We first emit the signal to the front 2 speakers by muting the rear speakers, and later we emit 2 bit sound from the back speakers by muting the front speakers. And the position we tested is like driver's right left, cup holder, co-driver's right left, and the back seat also similar to this front seat's position. And we define that the ABC, which is driver's right left, and the cup holder as driver's control area. And the phone is either put in pants pocket or the coat pocket. And to classify whether the phone is located at driver's area, we shift this 0, the ranging 0 to -5, so as to include this cup holder as driver's control area. So we conducted the following scenarios in our experiment. One is highway driving, which means we are driving on the highway at the 60 miles per hour, and there is noise, which are music playing inside the car, and also which I have like window open or closed in this case. And in this scenario, we only put the phone at the front seat only. And we also have another 2 scenario, which is phone 1, car 1, which is stationary, idle engine, and there is composition inside the car, so as the noise. And the third is phone 2, car 2, with stationary, no background noise case. Okay, let's first look at the highway case. Here we have 2 thresholds, which is uncalibrated and calibrated. For uncalibrated, it is the default threshold, which I mentioned is -5 centimeters. And the calibrate threshold is adjustable according to the dimension of the car. And in this case, we choose it as the best result that we can get, the corresponding threshold. And in this case, we have like around perfect detecting rate, which means we can nearly perfect detect the phone is located at the dark state if the ground truth is that phone is at dark state. And there is a few false positive rate. The overall accuracy is pretty high, it's about to 97%. If we next we look at the phone one, car one case with 4-channel radio, with simulated 4-channel radio system. From this we can say that we still achieve like around 94% detection rate with a few false positive rate. Overall accuracy is about 95%. And in the third scenario, we have a little bit worse results, but still the overall accuracy is like about 86 to 94%. Next, we look at the performance when we only use 2-channel system. And for this scenario, we only tested the phone at front state, and the accuracy is at around like 95%. For the second case, phone 2, car 2, and the accuracy is like around 90% overall accuracy. So if with only 2-channel system in the car, how we can what's the performance of our system if the phone is located at different states? So first, the detecting rate will maintain the same, which is about 90%. And because there are some cases the phone will located at the state behind the driver's seat. For these cases, it will cause false positive. However, according to the United Highway Administration database, we see that there is only 8.7% of the case that phone is located at the seat or behind the driver's seat. So at this false positive rate, we can say that we can achieve overall 90% of accuracy in the phone 1, car 1 case, and above 80% accuracy by using phone 2, car 2 settings. So let's get a closer look at the accuracy under different positions. In this case, we have positions from A to I, and the y-axis shows the overall accuracy classified the phone is at driver's control area or not. And the results show like this. For except the C, D, F, for other positions, we nearly have 100% accuracy. And for position D and E, it has around 80 to 90% accuracy. And if we look at the figure, we can find that the C and the D are coupled and the co-drivers left position, because these two are very close to each other. So it's relatively harder for us to classify these two positions. And as a result, it caused slightly worse results compared with others. So further, let's look at the ranging results at different positions, which is A, B, C, D, E, or in front seat. And this figure put the plot box, which shows this box shows that the ranging results after 30 rounds. And we can see clearly that for A, B, D, E, the ranging results can be perfectly separated. However, for this cup holder and drivers, co-drivers left position, there have slightly overlap with each other, which cause false positive rate. And further, we tested our method. We compared our method with existing approach in using like coordination-based method, in using coordination-based detecting method with short big signal. And we tested it in car environment with live site. And we have music playing at 60 dB and 80 dB respectively, which represent moderate noise and very loud noise. And for the method we compare with its coordination-based method to use chirp signal, it is claimed to robust to moderate noise, and it uses the coordination-based method to detect the signal, which means it coordinates the chirp signal with the recorded signal so as to detect the presence of chirp signal. And here is the results. We define the metric as a successful ranging ratio, which means that if the range error is less than 10 centimeters, it is a successful ranging results. And this blue bar shows the results of our method, and that one shows the coordination-based method and under 60 dB noise and 80 dB noise. Clearly, we can see that our method has 100% successful ranging ratio, whereas it's about 80% and 60% for the coordination method. So this method shows that our proposed approach is robust to very loud noise and also robust to multiple paths in entire environment. Okay, the last one is computational complexity, and the computational complexity is bounded by the signal that's needed for analyze. So we have two parts. One is short Fourier transform, and it has the other part is signal detection algorithms. Add these two together on ADP2 cell phone, we have like half second processing time for 2-channel system and about 1 second processing time for a 4-channel system. So which means that we can achieve actually real-time processing nearly real-time processing detection on the off-the-shelf smartphones. Okay, there are some limitations of our method. First, if you place the cell phone in a heavy intercoat or inside a full bag, it may muffle the beep sound, so that we cannot detect the beep sound in a recorded signal. The second is that if you place the phone at the passenger state, it will determine that it at the passenger state, but this is cannot support the incoming call resulting or message resulting. The third is that our method is do not have 100% accuracy, so it is less suitable for some applications depending on the perfect accuracy. The next one is that due to the computational cost, energy consumption could be high if you are continuously tracking the phone's position. Okay, there are some related work. For example, in driver distraction detection system, for this system, it mainly uses a specialized hardware to detect whether the driver is focused on driving or not, and also there are some applications that propose to handle the cell phone while driving. However, for this application, it's mainly based on the prior knowledge on whether the phone is used by the driver or not. And also there are some related work in acoustic position techniques, such as big beep system and also some other bad system. But for this system, some of them use dedicated hardware so as to get high accuracy of ranging information. And for other method, it use a coarse-grained ranging method with less accuracy, which cannot be used in our application. And finally, there are some in-car localization related work. For example, you localize the speaker inside your car, but it utilizes a specialized hardware, which is microphone array, and also some work in detect phone use by using like specialized antenna. Okay, here is the conclusion. We first propose a driver phone use detection system with following characteristic. It's a software solution without additional software. It leverages Acoustic and Bluetooth connection, and it's computational feasible on the off-the-shelf smartphones. And also we validate our approach with two kinds of phones in two cars. And overall, we achieved over 90% accuracy, about 90% accuracy with default settings, and around 95% of accuracy with some calibration with some concatenation. Okay, that's all.